Good night.
Hey, Michael.
Hey, could you just email me your slides?
Yep.
Just in case?
You got it.
Okay.
You can begin. I think, Eric, your mic is off. Turn it.
Okay, great. I'll get the sharing started. Just a moment. Okay. Hi, everyone. Great to be here. Thank you, everyone, for organizing this virtual conference in these challenging times, and hope everyone's doing well. Michael Braun, my co-author, is here. There he is, waving his hand, and I are really excited to share this work that we've been doing. As I get started here, the project has some really neat origin stories, but really what this talk is going to be about is called A/B test deception, in that we began by thinking about how are A/B tests actually practice from the perspective of the advertiser, from the perspective of the individual person running these experiments, and not the publisher necessarily. I'm sorry, this is still not sharing here. I'm sorry here. Take two is successful. Or not. All right, we have slides. You wouldn't think this would be harder than teaching, but turns out it was. Well, thank you, everyone. Now I'll just get a restart here, and I appreciate that. Michael and I are really excited to share this work with you, and that's because the project has come from a whole bunch of different angles. It is really, we're thinking about incrementality, a hot topic in industry and A/B testing, and we're thinking about the degree to which some of the representativeness in our experimentation are breaking some internal validity issues. So with that, let's jump right in. We're going to be talking about online field experiments in the context of social media, although it could be really anywhere online. specifically when the treatments are non-random. And we'll talk a bit about the literature, but I think a lot of us in the room know really the issues with some of the targeted advertising. But we're going to dig in a little bit of what specifically about targeted advertising is breaking some of our standard experiments. One thing that I think we're most proud of is actually providing a framework that is novel, that is actually going to help us better understand the effects of these ads, but specifically the different implications of this non-randomness. And so we will study then how the advertiser's inferences about the incrementality of the ad versus no ad differs across ads. And then we're going to illustrate that there is this bias. We're going to describe the nature of the bias with respect to trying to estimate the difference between A versus B, the effectiveness of ad A versus B on a target, on a particular audience. And it's a serious problem. And we are not going to conclude this talk with a solution. We are going to quantify the degree to which it is a serious problem and the degree to which one would, as a publisher, actually be disincentivized to solve this problem. So this is what we mean when we say A/B testing. Actually, you can think of two groups of people here are thinking of this problem. One would be actually academics, and the other would be advertising practitioners. So we'll start with some academic examples. People are running experiments. This is one of them, actually run in 2020 during COVID, Aratzi and Johnson, looking at the effectiveness of ads on Facebook in real time in the field and trying to answer underlying psychological questions. There are some constructs about consumer behavior that the authors and researchers here are trying to answer, and they're using this operationalization and experimentation on Facebook to do so. Here's another example. Some of you may know, Matz et al. In 2017 and PNAS. There were different psychological appeals used in Facebook ads. Experiments within those ads were run. Ads were randomized across. But unfortunately, as some of you are familiar with, Dean Eccles et al. In 2018 have a nice piece describing some of those issues. And we'll touch on that in just a bit. But this is what we mean. We also are referring to some aspects of creative elements. So here's an experiment. The city of Detroit was looking to see what are the different appeals to increase recruitment for their police department. And in this experiment, they not only tested different images, but also a series of different emotional appeals, whether it was about the self, whether it was about other, so community or career advancement. And there was a whole full factorial design here. And Michael and I were involved in the design of this experiment, but we're not going to focus on this necessarily. But the learnings from this is that if you are trying to extract creative elements like these, or anything about the creative itself, we're going to really focus on the issues at hand there. And the basic model you should have in your mind is just the basic regression model. Even though I'm talking about creative elements, really all of those are just slopes of some regression, and the slopes in practice in any nicely designed full factorial experiment, they're just differences between means of groups. So at the end of the day, even if it's a multivariate test or full factorial, or it's just an A, B, C, D, E, horizontal test, we're talking about comparing the effectiveness of ads by comparing means. Right? In this talk, we're going to refer to A/B test to mean all of those, although it really is just going to be, for now, just comparing two ads, A versus B. Platforms have created opportunities for researchers or practitioners to actually do this in practice. And perhaps some of you have run these tests. It's pretty interesting to go through and look at the different tools. But there's not just one test, not just one experimental setup. There's actually a standard A/B test as it's called on Facebook. This used to be called the split test, if you're familiar with it. Then there's the holdout test, or the conversion lift test, as it used to be called. And this is where they are randomizing, not just as the A/B test, they're randomizing some folks get ad A, some get B. But in the holdout test, they're doing what back of your minds, you might be thinking, well, no, we want the people who may have been targeted to get a random subset of those targeted users should be held out, and the others will be seeing it. Okay. And that's exactly what they're doing, and as well as a bunch of brand survey experimentations as well, so designs as well. But the practical problem is when you are buying ads, you are purchasing two services. When you place ads online, you're buying two services. One is the ad impressions themselves, right, to help you get outcomes as the advertiser. By outcomes, I really am going to be pretty generic at this point. It could be clicks, it could be conversions, it could be sales, it could be number of ads to cart or acquisitions. So one is impressions, but two is the actual algorithm that is targeting the ads to the right users. The fact that those two exist is great. This is what gives us a whole advertising technology industry. But the fact that those two exist right now, in the way that they do, really inhibits us from thinking about inferring causal inference from the A/B testing in the way that it's done today. Algorithms target both on observables and on unobservables with respect to the advertiser. A lot of the existing literature has looked at this problem, but has also looked at it only from the publisher side, or emphasized the publisher side. What we're trying to say is many of these unobservables from the advertiser side may be observable to the publisher. And in fact, publishers have, in communication with us, have actually said sometimes we don't even keep track of some of the aspects of data that are used to target ads in our own targeting algorithms. And the results are reported by only the observable factors with respect to the advertiser. I'll show you an example of that, but the targeting is still enabled throughout all of these so-called or sometimes semi-randomized experiments. It is a practical problem. I want to just recognize some of the folks who have really been doing this work at the intersection of industry and marketing academia, really on the cutting edge. When targeting is still enabled during these experiments, we've seen a bunch of innovation. Johnson et al. Have really innovated with ghost ads several years ago, thinking about the incremental lift of ads measured specifically, serve this customer this ad versus not. And Eccles et al. Make the point in with respect to the Matz paper to say, hey, there is this issue where when we run an experiment, just A versus B, there's covariate imbalance because the folks that are seeing A are not the same as the customers who are seeing B. And Gordon et al. Recently focus on lift tests at Facebook, much like the ghost ads at Google, where we're saying that's really the randomized controlled trial. That's the gold standard. These holdout tests, these lift tests. Okay, I want to now introduce two new terms, sort of new terms to the discussion. And one is response heterogeneity, meaning among targeted users, simple, really heterogeneity, but it's the interaction between some users are more responsive than others, and some ads generate more responses than others. So it's that interaction between ads and users in terms of baseline conversion rate propensity. And the other is divergent delivery, which is an interaction between ads and users in the targeting algorithm itself. So algorithm may decide to serve some users at a higher rate versus others. And it also might decide maybe the ad should be shown more than the other ad. But the interaction of those two, we're going to call divergent delivery, as in two different groups of customers are getting served differently, or ad A is being delivered differently than ad B is being served. And what does that result in? It results in plots like this. So in the Detroit Police Department example, you can see the proportion of individuals on Facebook exposed who were female. Across the different ads varies substantially, very substantially. And it may not be a surprise, but the domestic violence and data analyst roles had women in them. The patrol had a man in the front, a woman in the back. ESDC and PAL are just really placebo public service announcements ads, and not surprising, the ESDC also featured a woman in the ad. But these are just observable factors. So if it's this strong on observables like gender, imagine all of the factors that we don't get to observe that were used in the targeting algorithm, but we as advertisers don't get to see. So the theme of this talk, as I kind of kick off into the main framework, is because of the exposure to the experimental conditions is not random. These A/B tests conducted in a targeted advertising environment generate biased inferences about the effectiveness of the creative elements of the ads. Specifically, when the results are aggregated across those unobserved factors, that's when we generate this bias. And again, when I say creative elements, you can think of them as different attributes of the ad, but it also can just be the bundle of those creative elements of the ad. But we want to separate that out from whether the targeting algorithm was good at sending these ads to certain users. So separating the creative elements of the ad from the work that the publisher's targeting algorithm is doing. We're going to start with the standard model of really compliance here in the potential outcomes framework, which we'll lean on heavily. And that is, we're going to work with Z as our random assignment to the ads. The standard treatment versus control. This is the binary situation where it's just treatment versus control, 1 or 0, and compliance when it's not random, exposure, sorry, would be 1 or 0. Okay. And in that standard model that we're going to now have to improve upon, we end up getting something like this, where there's awkwardly 3 conditions. The fourth cell of that 2x2 doesn't quite make sense in these contexts. And so, well, we can talk about the best estimate of the causal effect, because the true causal effect is really for any user I, it's going to be the potential outcome difference. But this can work when there is a treatment and control. But when we actually have a campaign of several ads, multiple ads, and targeted differently, so the exposure mechanism differs across the treatments, even just the notation breaks down. And so we're going to propose just a generalization of this approach. And I don't think this part is earth-shattering. We're not pretending it is, but laying it out thoughtfully, carefully, and deliberately here is something that hasn't been done yet in our literature. So the advertiser is going to define an audience. And this audience, for those of you who have run Facebook ads, can be quite specific. You get to choose whether I want to serve 25 to 40-year-old men in Ann Arbor, Michigan, right? That is a demographic. You could go more specific to those who watch basketball, right? Or more broad. So that's when we talk about audience, that's what we're referring to. Anything on observables. X, therefore, is everything else on unobservables. So users within that audience differ in many unobserved ways, right? And so then those users get randomly assigned to Z, the treatments. So here's our potential outcomes framework in the case of this ABC test of 3 different Zs, where we can think about and define a notion of potential lift. And we're borrowing lift from the really practice and our literature, where lift is really the difference between if you had seen the ad versus if you had not, what would you have done? So we're going to define that as lambda Z. And again, it's potential. So the superscript 1 and 0 in the parentheses are following the Rubin causal model, where it is the hypothetical potentials that we can get. But that's just lambda for Z. We could get lambda for A or B or C. What we're actually interested in is the difference. And that delta AB, the difference between lambda A and B, that's what we're after. This is the difference that allows us to infer the effects of one creative element versus another, one ad versus another. That's what we want. And so in a split test, a standard split test, you can see some of these diagrams. Hopefully they help kind of set up and visualize this. Michael and I definitely geek out over our visualization, so happy to talk about those. We're going to talk about targeting because you now need to target. This next step, you've randomized now as targeting. Tau is in red here, 1 or 0, and you can see the red ovals, outlines around the ovals, designate the users who were targeted. So some users within A get targeted, others within B, others within C. And for here, we're going to really just say that for this design right now, that exposure D is just equal to targeting. We'll relax that in just a second. And you observe just the YI1 for those targeted users. And you can see immediately that, well, the targeted users in A are different than the targeted users in B than C. And so you need one step further. And so the split lift test takes care of this to some extent, but not fully. It essentially creates a holdout, randomized controlled trial holdout within each ad. And so Gordon et al. Really focus on this kind of lift test where you have within ad A, the users who are targeted to get A then get conditionally re-randomized, which is that blue letter R, into either the treatment or the holdout. And the subsequent lift can be calculated, which might be the, we'll call the lambda A targ, which is the lift estimated on the targeted users, taking the difference between lowercase a1 and a0, the outcomes for those respective groups. And this is exactly the setup of this multi-cell conversion study, or now called the A/B test with holdout. And just think what's wrong with that comparison is, well, it still doesn't solve the problem that the users targeted with A are different than the users targeted with B, or different than the users targeted with C. Again, this X here, we're using X not for the observables, but any unobservable characteristic out there that could have been used by the Facebook targeting algorithm, but is unobservable to the advertiser. It's why we're using even the letter X there. And so we're going to now walk through the ways in which response heterogeneity and divergent delivery can be defined based on this framework and operationalized. And we'll close with a simulation to illustrate the degree to which this actually can be quantified, and the degree to which and the conditions under which we can get reversals of inference. So targeting across ads, we're going to just simply use two groups of users, X for now. We're going to call them quarks and protons. You might see another P and Q pop up there. We're debating the name still. And so we're going to define gamma to be the baseline, the prior mixture of the population that is a type P person, a proton versus quark. Then there's the conditional targeting probabilities. Well, these are the probabilities that if you were assigned to ad A and you're a proton, what's the chance that you're going to get targeted? That's going to be phi. So that's really what the whole oval represents to some extent within each group. And we can also target across the other side. So we can look at the A versus B users. There's a marginal effect there. Some of those might get targeted more than others. So that's going to be alpha for A, B. Tau is for targeting. And that pi is the poets and quants groups. There's our poets and quants, or protons and quarks, where we're looking at what is the proportion, relative proportion of targeting activity towards the protons versus the quarks, or poets versus the quants. Divergent delivery is the interaction of the two. It is the degree. It is the odds rate. It's the comparison of the odds. It is the odds ratio. Right. The A poets, the degree to which the A poets get targeted versus the A quants, compared to the ratio of how the B poets get targeted versus the B quants do. But targeting changes the mix of the customers. It's all about the mix and heterogeneity of the customers. So while we start with a group where we have just the two squares, just the light blue and light red, excuse the color change. We like these graphs a bit more. From there, it gets targeted down to just the oval, and that oval no longer represents the overall rectangle. I just want to emphasize, you might be thinking, well, you don't care about the whole audience. Well, in this case, we're defining the audience by the variables that the advertiser chose for their campaign that they got to select. And the exact same thing is happening with B. Again, that gets shifted in a different direction with a different mix of protons and quarks. And if we ask the question, well, what's the chance that any given proton who is randomly assigned to A does in fact get targeted, it would just be this equation, that little semicircle oval over that area. So all of these are area equations. The overall marginal probability of serving of getting targeted if you were assigned to A would be this. The overall marginal across all would be the sum of both of those ovals, targeted regions over the full area. And then this very last ratio is the sigma PA, meaning among those who end up getting targeted with A, what fraction of them are in fact protons? And that can be compared, this ratio right here can be compared to the gamma P, which is just the initial of the prior mix before the targeting occurred. And this actually is exactly a prior posterior relationship. And we could then do this with user response, not just targeting. And so instead of the kind of working off the tau, we can now think about, well, we're now interested in the tau and the phi. We're interested in this conversion rate, theta. And so the exact same notions can be defined. We can define the lift just for, say, the protons who were targeted with B as lambda PB targ, as the difference between the potential conversion rate for one group if they were in fact exposed, and the potential average conversions for the other if they were not. Critically here, then we have an aggregate lift. I want to just emphasize this aggregate lift of lambda A, that's the only thing that could possibly be reported in even the best designed experiments currently on Facebook and these platforms. That is, lift A is already could be estimated from the split between any group of users in A and the holdout, aggregating across everything going on with the different subgroups themselves. Okay. That lift for any Z or A, what we care about is the average treatment effect for the audience as defined by the advertiser. And so that ATE is going to be really the prior mixture of the gamma P and gamma Q, because the advertiser cares about that whole square, that whole rectangle, not just those users that got targeted. By contrast, the lifts and the difference between lifts for these ads among just the targeted users will not contain the gamma P and gamma Q alone, but instead the sigma P Z and the sigma Q Z. And that's the posterior. That is that visual equation that we're just working off of. And so the targ AB, the delta targ AB, is really what happens if you run one of these split tests with holdout. So you have an AB test with holdout, and you just say, well, I have a lift for ad A, and I have a lift for ad B. Why can't I just take the difference between them? They're different groups of people. And so that bias, the fact that there is a difference, because we can compute these from the observed data for the targeted groups from a split lift test, but we care about, as an advertiser, drawing inference about the broader group of the audience that is not represented in these targeted groups. And so we're going to define the bias here. Now, I want to be clear, it's not just because the targeting is occurring. That itself isn't the problem. It's that the targeting occurs differently across treatments. And so this bias is going to lead to an over or underestimation of each of the ads aggregate lift estimates. And that then creates a bias in the difference, really the key causal question in the A/B test, this delta A/B. So we're going to begin actually now talking about an example here that you may have known as Simpson's paradox. It is Simpson's reversal because it's really not that paradoxical if it happens so often. And here's the premise to illustrate the way that our whole framework can kind of play out here in a fairly reasonably common example. If the lift of A is higher than the lift of B for all types of users, so for the protons, they end up clicking on A more than they do B with respect to compared to not having either of the ads, and for the quarks, they also are have a higher lift for ad A than they do for ad B. Simpson's reversal means that, well, if you only get to aggregate at the level of A and B and not protons and quarks, it flips. And so suddenly now ad B's lift overall appears to be better than ad A's lift, even though we know for each group, and there's only two groups, that's not the case. Typically, when you've seen Simpson's paradox or Simpson's reversal, you've seen it and you just need to dive a bit deeper into the data and slice it and do crosstabs and just look at the heterogeneity, and you can see how, oh, there's a heterogeneous effect. This difference differs across groups. You don't get to do that here because the protons and quarks are unobservable to the advertiser. And so the targeting process doesn't just could cause a Simpson reversal, but it's not really a crazy circumstance, as I'm about to show, for it to occur, and the advertiser just won't know. Right, we can mathematically pin down exactly the expression of when it is. Punchline here is that it's really about the mix, which is captured by sigma. So we're operationalizing this, visualizing it as sigma QZ down on the row on the x-axis is really just the probability that you happen to be a quark given that you got targeted with the ad. And the red line is following. So if for all protons in the group, they are responding more to A, and all of the quarks in the group, they're also responding. They would respond more to at A, but because of the particular mix for A, where there's only 15% quarks that end up seeing A, and among all those that are targeted with B, 60% are quarks, the resulting lift estimates are such that A is actually lower than B. Again, it's all about that posterior mixture as a difference from the prior mixture. Again, we could kind of, it really is just about when you have this fairly kind of slightly smaller difference in ads, in ad effects, but extra targeting, that's when you get this Simpson's reversal. And if you think about the way quite a lot in practice ends up working, small effects and lots of targeting is precisely what happens. So
Eric, you have 10 minutes.
Perfect, thank you. Perfect. To describe these responsiveness and targeting policies, we're now going to get into what's going to build to a simulation. We can see some just quantification of these results and where they get turned off and where they get exacerbated. Again, just a quick notation check. The tau is for targeting, the y is for outcomes, the alpha is for the A versus B ratio, and the pi is for the proton versus quark ratio, where the rho is this response heterogeneity and also the divergent delivery. I think I already kind of walked through these marginal probabilities. I'm not going to hit these too hard right now, but just want to emphasize that rho really is the odds ratio. It is we could think of it as those phis, or we could also think of it as with respect to among all the people that got A, what fraction of them were protons divided by what fraction were quarks. And among all those that got, and how does that ratio compare to all those that got targeted with B, and how many of those were protons and how many of them were quarks. And we can do this all with the outcomes of heterogeneity. So the in this case, the theta PA1 and theta PA1, each of these is the conversion probabilities, the expected probability of each of the user and types. But we can then actually do a similar kind of reverse where once the mixture of converters is exposed to each ad, we can flip this around and just express it as a different type of ratio. How to visualize? I have an app, a Shiny app to show, and for folks interested, we can talk later in the conference, but I don't dare to test my luck here and try our Shiny app right now in real time, given my opening. But here's how the different targeting parameters. So just by 3 parameters, this alpha, pi, and rho, we're going to describe targeting. This is our protons and quarks in A and B, 2 by 2, that we've been referring to. The blue line up and down is really the A versus B randomization, and the green line divides the quarks and protons. 1, 1, 1 is all of the ratios are 1. So there's no divergent delivery, there's no response heterogeneity. The protons are targeted as frequently as the quarks, and the ad A is served up as frequently as ad B is. But if we shift that and now increase pi, tau, just a little bit, that is defined as protons over quarks. So if pi tau gets larger, the protons just get served with more ads of both types. And in fact, if rho tau and alpha tau are also still 1, then they're going to get served with both types of ads, but equally so. So this is not a case of divergent delivery. That rho tau is still 1. And we can see how we start kind of combining. The alpha does this. If we do just the interaction, this rho, while the alpha and pi are 1, so on the margin, ad A is shown as much as ad B, and on the margin, protons are targeted as much as quarks, but actually the interaction is quite large here. And so this is what divergent delivery looks like, even when you have the margins of targeting to look like they're balanced across protons and quarks and A's and B's. And here's how it looks when we start creating a more realistic imbalance. Divergent delivery is quite large here, but what it's showing is you're not really getting many of the protons who were exposed to ad B at all, although you have an estimate from them. And the mix of people then in the aggregate lift estimate of B, well, you don't get an estimate of just the protons who saw B. You only get an estimate of those individuals who were targeted with B. And so you would never know that your group from which the ad B lift was calculated actually contained almost no protons. But when calculating the aggregate lift for ad A, it actually had a substantial amount of protons. And in fact, just overall more. And we can see how we can play around with these a whole bunch more. Don't need to keep going through those, but let's jump into the simulation. And each of these is a different world of characterizing the targeting algorithm. And I can do each of these analogous figures with analogous alpha, pi, and rho for response heterogeneity. And so it's pairing up these variables, these 6 variables now in combination to now think about how the interaction between heterogeneity of the underlying population and the targeting algorithm's use of that heterogeneity is going to influence the bias that we see in getting to this simulated truth, which would be the 8, versus the best estimate that the advertiser has, even from running the multi-cell lift test, these A/B tests with holdouts. The best they can still do is getting at that delta A/B target. So jump right in here. We've actually simulated these with C, but I'm just going to show them with A and B. Everything is 1. There's no bias. Not surprising. We're going to look at this scale. Left to right is going to be pi tau. So on the left means there are more quarks targeted than protons, and on the far right it's more protons targeted than quarks. And the error is the difference in the deltas, which themselves are a difference in aggregate lifts, which themselves are a difference in expected potential outcomes. So we're looking at a difference in difference in difference here. Now let's introduce some response heterogeneity. So we have a heterogeneous group where the protons, meaning this large area, would mean that the protons are who are targeted with A, just their propensity for even responding to A is much higher than the proton's response to B. And you can see that the QB combination is kind of on the diagonal there, is also larger. So the quarks respond to B more than they would respond to A. But the other two parameters are pretty much at 1. And so what we can see here is that for different levels of targeting, the error increases. Point you to the green line. That is the degree of targeting that's maximum here, at least on these 3 points. That generates the largest bias. Why? They're in row tau of 8. They are targeting exactly aligned with the degree of heterogeneity. And so is someone chatting? Nope.
Eric, your time is almost up.
Yep.
So we'll have to just conclude.
Okay, perfect. And so we can do this, and as we walk through all of these simulations, we've got the all of these. We can point to the Simpson's reversal. The concluding slide I want really here is for you to see that there actually is a whole lot of dollars behind this, because we can actually then compute a strategy that would not target differently by each ad. And instead, it would not have divergent delivery. So we call this disabling divergent delivery. And across different conditions, we estimate and can really actually prove under this framework that by disabling divergent delivery, the publisher and perhaps advertiser would have about 10 to 20% less in revenue from the entire advertising campaign that includes this experiment. That then brings us to this conclusion of, why isn't this happening in practice? Why aren't platforms like Facebook and Google offering to create this extra level of randomization to say, listen, we are not going to divergently deliver ads to different groups of people. We're not going to take 2 randomized groups and then serve them ads differently. Well, it costs them quite a bit of money to not do so. And so how one might split the pie, that deficit, whether advertisers would have to pay for such a service or for publishers to eat the cost, we don't know, but we find that to be an interesting question. But really, it's this paper is trying to stake some claim in saying we're getting really close on the online advertising experiments world, but we still have a way to go. Thank you.
Thank you. Brett, you can share your slides.
Brett, you're on mute. Brett, you're on mute.
Got it. So I'm working on sharing my screen, but it's not, it doesn't seem to be going through. Maybe the same thing that happened to Eric at the beginning.
Yeah, Brett, I had to give permission all over again to Microsoft Teams to control my computer, even though I've given it to them many times.
Yeah, I thought I did.
Yep, me too.
Let me try something. I'm going to quit and reopen it. So I'll be right back.
We could answer questions while waiting for Brett to come back.
So let me ask a simple question. You don't propose any way to overcome this, except for Facebook to change its methods.
Well, I would say that
right, or did I lose something there?
No. So I'd say the way that we are trying to propose an approach that would overcome quite a bit of this bias would be to have this situation where you target the group of users first, and then you randomize across your ads. But the mix of users then that see each of your ads will be identical. So to your point, yes, that would be changing the way Facebook would run or Google would run these experiments.
So there's no statistically way of doing this because we just don't know the population. I mean, it seems to me the population is not the same from which you're sampling. That's what you're saying, right? Roughly speaking.
Yeah, there's no way.
Different populations, and that's a problem.
Yes, but it's not just that they're different. They're different in ways you will never know.
Well,
all right, can you see my screen now?
Ron, I think that disappointing tone is ours as well.
Okay, no, it wasn't meant to be a criticism. It was to make sure I understood what you were trying to do. No, 100%. I like the work. I want to understand it correctly. That's all.
No, I appreciate it.
I want to wait for Brett. I shouldn't be taking his time. Sorry.
All right, can you see my screen now?
I can't see your screen.
You cannot?
No.
Neither can I.
No.
I can't see you on video.
Put it up. Can you mail it to Eric and he can put it up, or what? I don't know.
I'm happy to do that, but
so it looks to me like it is sharing, like it says that it is.
Mm-hmm.
As a quick solution, maybe emailing to Eric might be a good solution.
All right.
That's plan B. That could be a plan B. So, well,
you could put it, if it's on Dropbox, you could put a link in the chat or email. I'm also anticipating whether I'll have problems presenting.
Yeah, Brett, I hear that in your voice, Brett.
Hope you're planning on staying for my talk.
Yeah, of course. I got to experience it first. So. Right.
So I did just email it to Eric.
Now I see it.
We see your whole screen.
You do see my screen?
Yeah, now we can see it.
All right.
Yeah, you're full. Okay. Perfect. Yep.
Okay, great. So, all right, thanks a lot for inviting me. Sorry about that technical glitch. All right, so let me start by saying I'm not a person who researches targeted advertising or does it myself, so I'm going to give the outsider's perspective. I did learn a lot about it from reading this paper, so I really enjoyed reading the paper. So I was trying to think, what would I do that would be wrong according to these authors? So I tried to think of an experiment I might want to run, and so here's my experiment. I have this theory about how ad effects work in the hotel industry, and so I want to test two different hotel ads against each other. And one of them, I say, this is 5-star perfect TripAdvisor rating. And then the other one, here's your like personalized discount. All right, so I'm trying to measure something like how important is your star rating in dollar terms by directly comparing it to a personalized discount. All right, so this is my brilliant study. We're gonna learn so much from this. And so we go on Facebook to run this experiment, and we show a bunch of people this TripAdvisor ad. And Facebook is very sophisticated, so it creates two groups of viewers who are sort of matched. And so we've got a control group and a treatment group, and they're perfectly evenly matched, so we can measure the lift properly without any concerns about targeting. That's sort of like the ghost ads idea. And then I try to run my personalized price discount ad, and we get a different perfectly valid experiment where in both cases we've got a treatment and control group that are matched, but they are different between the two conditions. All right, so in this case, we might be concerned that the AI inside the targeting algorithm knows that there's something in the ad on the right that is price discount, and so it sort of tags that, and it's going to target that to people who it thinks are going to respond to a price discount. And so we know that Eric is very cheap, and so it's going to be more likely to send the Eric group the price discount ad compared to the TripAdvisor ad. All right, so these are both valid experiments. So if you're just trying to measure the effect of, which ad is better, then you don't care. But if you're trying to measure the difference between the two conditions, because you've got some kind of academic theory, then that's going to be biased by the fact that we're going to different groups. So even though we've run two valid experiments, the difference is not going to be valid. And looking at observable characteristics don't help, right? So just look at these guys. It's two white guys, kind of similar in age, similar in education and income. They live in the broader Midwest of the U.S. if you extend it from North Texas to Michigan. All right, so we can't tell the difference between these two people based on anything we observe about them. It's only unobservable differences, and that's what it's being targeted on. All right, so this can be pretty bad, especially in the difference between the two ads in the treatment effect on the treated, but it's going to be even worse on the average treatment effect because there's going to be different populations in the two groups. All right, and it's even possible that this can reverse the sign of the overall effect, where ad A works better overall for every sort of subgroup, but because of the difference in targeting, it shows this to sufficiently larger number of one group that it reverses the effect. All right, so here are my comments. That was my overview. As the authors are extremely upfront about, this sort of general point has been made before by some other people who said, this is potentially a problem. So the contribution here is really that they fully flesh out all the details in a formal model where they show exactly how all the pieces fit together and in a nice formal way. I think it's a nice contribution. It makes things very clear. The paper is very clearly written. I found it very easy to understand, and I think it's clearly correct. So I'm sort of not going to try to attack it in any way. So I just want to suggest that the results could be presented in a clearer way and maybe put to better use for people who are actually trying to understand how big of a deal this is for their specific settings. Okay, so they show a huge set of possible cases with simulations. Eric went through like 3 or 4 of them, but in the paper there's like dozens, and I found it hard to sift through them and say, well, which one of these are really important? And if the punchline of the paper is never ever do this, that's great because that's like the clearest possible takeaway. But if the punchline is something a little more subtle, like here are the exact situations where it's going to cause a big problem, then I wasn't getting that. I think you need to sort of hold the reader's hand a little bit more and say these are the empirically relevant types of parameters that you should be worried about. Okay, so another comment is that they focus on the bias in the average treatment effect. And I was just wondering, how much do we really care about the average treatment effect as opposed to the average treatment on the treated, especially for actual advertisers, because there's always going to be some targeting. And they use the example in the paper of, well, what if they want to learn something about how different groups respond and then run that in a TV ad. But a TV ad is not that comparable to a Facebook ad. And so there's always going to be some difference when you move from one setting to another. And so maybe they're overcomplicating things by focusing on the difference between these two things, given that we're always going to have change in the outcome when we move to different settings. I was also wondering how, as a non-practitioner, how likely is the sign reversal, the Simpson's reversal, in like a real practical setting? So I was looking at this figure, and We've got lift curves sort of for the two user types, protons. Yeah. So for the type Q, the lift is 2.5 times higher than for type P, and for the other ad, it's 8 times higher. And so I was thinking, if the targeting algorithm is any good, then wouldn't it like only show it to type Q? Like, why is any type P person getting this ad, especially for ad B, if there's an 8 times higher response rate among type Q? So it seems like this, I just don't know as a practical matter if you're going to really show it to a lot of people in type P group, let alone a majority of them, as it is showing for the ad A, if this difference in lift is so stark. All right, so and kind of going back to this focus on the ATT, this possible solution is this non-divergent delivery, which says if you want to, maybe you say, I'm an academic, I'm running an experiment, treat all my ads as a single targetable unit. You know, this is going to work, and it's only in the case where you're interested in the ATE that it's not going to work. And so, you know, it seems like maybe you should just make that more clear, or put more results up front about the cases where we don't care about the ATE. And then in sort of generally speaking, focus on the most realistic cases and sort of walk through those first. And then, you know, you've got all the cases in the paper, which is nice. But, you know, we probably only care about like the more realistic ones where, you know, one group has a higher conversion rate than the other, therefore they are targeted more, and, you know, with some kind of reasonable ratio. And I thought maybe you could go to the paper by Gordon and Zettelmeyer and their co-authors at Facebook and see if there's some parameters that you could take from that. That would be sort of a way of sort of filling in what is reasonable here and what is not reasonable. You know, and I presumably you have some data from this Detroit experiment. I didn't see that in the paper at all, except for motivating the idea. But maybe there's some data you could use to sort of define what's reasonable and what's not. In particular, I was thinking that a lot of the interventions or treatments that would vary across ads are likely to be subtle.
I think you should conclude.
Okay, so I'll just cut to the very bottom. You know, I feel like the people who are going to need this are the people who are like doing behavioral research, and they're like, who's going to respond to my ad about charitable donations? Is it going to be like whether I use the social pressure or I use some other thing? So, you know, they're the ones who need this. So can you send it to them, please? That's it for me. Thank you.
Thank you.
Thank you, Brett. You hit on some of the issues that I would say we've been most concerned about, and did so extraordinarily well. So really appreciate that careful read.
Yeah, Brett, thank you. That was just smack on the